There is this incredibly common scenario that I think almost all of us have experienced by now.
Oh, definitely.
You sit down at your computer, you take a massive PDF, maybe it's I don't know, a dense financial report, a legal contract, or just a really long stack of your own personal notes, and you upload the entire thing into a generative AI prompt.
Right.
You hit enter, and you sit back with this very comforting assumption. You just assume that the AI has absorbed all of that text, filed it away perfectly in its digital brain, and is now holding on to this flawless photographic memory of every single word you just gave it.
Yeah, it genuinely feels like you've just handed a genius an encyclopedia and they instantly memorized it cover to cover.
Exactly. But today, well, we've got a fascinating stack of sources to challenge that exact belief.
We constantly anthropomorphize these machines.
Yeah.
We hand them huge documents, they give us coherent answers back, so naturally we assume they're functioning like perfect digital filing cabinets.
Which makes total sense from a user perspective.
Totally. The prevailing belief out there is that an AI's internal memory, what computer scientists refer to as its embeddings, is this pristine, high-fidelity copy of whatever input we provided.
Right. But our mission today is to take all this dense research from a foundational state-of-the-art paper out of IBM Research, complete with their testing methodologies and raw data tables, and just absolutely shatter that massive assumption.
Because the data really does shatter it.
It really does. The photographic memory we think these large language models have is actually a complete illusion.
Okay, let's unpack this, because peering under the hood of how AI actually stores the information we feed it is absolutely mind-blowing.
It really is. So the IBM researchers started by testing a very fundamental question, right?
Right.
What does it actually mean for a neural network to have a good memory in the first place?
Right, how do you even measure that?
Exactly. And in the context of machine learning, a perfect memory is defined by a mathematical concept called invertibility. Invertibility, meaning if I put something into the model and it compresses it down into its internal embedding, I should be able to reverse engineer the process to pull that exact same text back out.
That is the ultimate test, yes. If a model's memory embedding genuinely contains all the necessary information from your document, you should theoretically be able to perfectly reconstruct or invert the original input text using nothing but that embedding.
Okay, so how do they actually test that?
Well, they didn't just casually ask the AI to repeat things back in a chat window. They built highly complex trainable decoders, specifically designed to extract information from the frozen embeddings of standard language models. And they threw a massive amount of computing power at this extraction process, like up to 96 V100 GPU hours.
Wait, 96 V100 GPU hours. Just to pause on that specific metric, that is a staggering amount of brute force computational muscle.
Oh, it's massive.
We are talking about running some of the most powerful, energy-intensive hardware available for days on end, purely to squeeze the model. Like, they were practically begging the system, using every ounce of modern hardware, to just regurgitate the text it was originally fed.
Right. They gave the extraction process every possible advantage. And the data they got back from those extraction attempts was, well, it was shocking.
I can imagine.
They tested standard causal language models. These are the typical models you and I use every single day, which are trained primarily on next token prediction, meaning their entire job is just guessing the next word in a sequence.
Okay, causal models.
Yeah, and they also tested models specifically built for retrieval. To grade the memory retention across the board, they use something called a Hamming metric.
Let me make sure I'm wrapping my head around this Hamming metric. It sounds a bit like a teacher grading a massive multiple choice test token by token, right?
That's a great way to think about it.
Like, if the original input word was revenue and the inverted recovered word is revenue, it gets a point. But if it guesses profits or money, it gets 0 points, even if the meaning is basically the same. It demands absolute perfection in token identification.
That is a perfect way to visualize it. The Hamming distance measures exactly how many substitutions are required to turn the recovered text back into the original text. It demands granular token-for-token accuracy.
So it's strict.
Very strict. And when they graded these causal models using that strict metric, they found that they only successfully reconstructed about 5% of the input tokens.
5%.
Just 5%.
That is genuinely abysmal. I mean, if I upload a 100-page legal document, the AI is effectively retaining the exact wording of maybe 5 pages and completely losing the other 95.
Exactly, it's gone.
It's like, imagine a student cramming for a massive history test. But instead of reading the whole textbook, They are only looking at the very last word of a sentence to guess the next one. George Washington crossed and they guess Delaware. And then the student immediately throws away the entire paragraph about the Revolutionary War because they don't think they'll ever need it again.
That's a really accurate analogy, honestly.
But wait, if they're tossing out 95% of the input, how are they functioning at all? How are they answering our questions if they literally don't remember what we just handed them?
Right, and this raises such an important question. It points directly to the core architectural flaw in how these models are built and trained. The reason they function, and the reason they forget so much, comes down to the mathematical nature of next token prediction. It is what mathematicians call a many-to-one function.
A many-to-one function. So you take many inputs, like a long sequence of words, and you forcefully narrow them down to just one single output, the next predicted word.
Exactly. Think about the structure of human language. If I say, the dog chased the... you intuitively know the next word is probably cat or ball or squirrel.
Sure.
You only need the last 3 or 4 words of context to make that prediction. You absolutely did not need to remember the 500 words of context that came before it in the story.
Oh, I see.
Because the AI's entire architecture is optimized solely to minimize its error in predicting that single next token, its internal objective function practically encourages it to discard older information.
Because keeping it is just a waste of energy.
Right. Retaining perfect, lossless memory of 1,000 words ago doesn't help it guess the very next word right now, so it throws that older data out to save computational effort and memory space.
So amnesia isn't a bug in the system, it's a feature. The model is literally trained to forget. It's functioning exactly as designed by aggressively filtering out anything it deems unnecessary for its immediate guessing game.
Filtering necessitates forgetting. It is an unavoidable byproduct of causal training. But if the fundamental nature of next word prediction is destroying the AI's memory, the researchers realized they had to look for a completely different kind of architecture.
What kind of architecture?
An AI that isn't trying to guess the future, but is obsessed with preserving the past. This is where they bring in autoencoders.
Autoencoders. Okay, how does their underlying architecture differ from the causal models that are, tossing out all our data?
Autoencoders are models that are explicitly trained not to guess the next word, but to regenerate their exact input. Their sole objective function is input reconstruction.
So they just copy it.
Basically. They take the text, compress it into an embedding, and then their own decoder tries to recreate the original text perfectly from that compression.
Yeah.
And the data from the paper shows that when you train an autoencoder this way, it achieves nearly perfect memory formation.
Really? How perfect are we talking?
We're talking up to 99.6% token recovery accuracy. Yeah, they measured this using an entropy ratio, denoted in the paper as H sub R, of 0.999.
Let's break down that H sub R metric for a second. In information theory, entropy is essentially a measure of unpredictability, or like the raw amount of distinct information in a sequence.
Exactly.
So an entropy ratio of 0.999 means that 99.9% of the original structural information from the text is perfectly preserved in that compressed embedding. It's as close to a flawless digital zip file as you can theoretically get.
It is remarkably efficient.
Yeah.
But, the researchers knew that a high score on paper isn't always enough. They had to prove this wasn't just a trivial trick by the neural network.
A trivial trick, like the model is just cheating on the test somehow, instead of actually learning how to compress and remember the information.
Yeah, exactly. A trivial encoding would be if the model just mapped one input word to one specific mathematical element in its embedding vector, like a simple, rigid one-to-one lookup table.
Okay, I follow.
If it does that, it isn't actually understanding the context or learning the complex semantic distribution of language. It's just doing a dumb copy-paste. To prove the autoencoders weren't cheating, the researchers ran a fascinating test. They fed them pure, out-of-distribution gibberish.
Gibberish?
Just uniform sequences of random tokens that don't adhere to any grammatical or semantic rules of human language whatsoever.
Let me think about the logic there. If the autoencoder was just using a dumb one-to-one lookup table, basically cheating, it wouldn't care if the text was Shakespeare or complete random gibberish. It would just map random word A to slot A and memorize it flawlessly regardless. So the fact that they are running this test makes me assume it failed the gibberish test.
Oh, it failed spectacularly. The autoencoders exhibited very high cross-entropy loss, meaning they completely broke down and couldn't reconstruct the random gibberish at all.
Which is actually a massive victory.
It really is.
Yeah. The fact that it failed on random noise proves that it relies on the predictable patterns and semantic rules of human language to actually compress the data. No underlying linguistic pattern, no memory. It proves the autoencoder genuinely learned the underlying data distribution.
Precisely. The models were performing near lossless compression based on the actual semantic structure of the text, not just acting like a mindless hard drive.
Okay, I'm looking at these test parameters, though, and I want to push back a bit on the scale of these initial experiments.
Sure, go ahead.
We're talking about standard, maybe somewhat smaller models to prove this concept. But I'm looking at the modern AI landscape, and the industry's answer to literally every problem right now is make it bigger.
That is the trend, yes.
I mean, are we just looking at small, weak models? What if we just throw more compute and parameters at it? Doesn't a massive model naturally have a massive memory? I'm looking at models like BERT Large, Llama 3.11b, and Quinn 3.6b. These are massive heavy hitters.
It is the most logical hypothesis to make, honestly. And it aligns perfectly with how tech companies market their newest models. But the IBM researchers tested exactly that hypothesis. They took those off-the-shelf giants, BERT Large, Llama, Quinn, and ran the exact same inversion tests on a 512 token context window.
And did the sheer scale of the parameters fix the amnesia?
Not at all. The massive models only saw a modest single-digit percentage increase in memory accuracy compared to the smaller ones.
Wait, really? Single digits?
Yeah. For instance, Llama 3.1 only recovered about 5.3% of the tokens for a 512 token context.
5.3%. Wow.
It turns out that scale absolutely does not fix the fundamental architectural flaw. If you train a model on next token prediction, it mathematically does not matter how many billions of parameters it has. Its objective function still incentivizes it to throw away input information.
So just feeding a model a trillion more words and a billion more parameters doesn't change the fact that it's fundamentally built to be a skimmer, not a careful reader. A bigger skimmer is still a skimmer.
A bigger skimmer is still a skimmer. The architecture is the bottleneck here, not the size. However, the data does reveal some really fascinating nuances regarding the limits of that architecture. Specifically, what you feed the model and how much you feed it at once heavily influences its memory retention.
Oh, interesting.
Yeah, context size matters immensely. When they tested much shorter prompts, say 16 or 64 tokens instead of 512, the recovery accuracy went up significantly. Like a 16-token prompt on BERT Large recovered over 40% of the tokens.
Okay, so smaller, bite-sized chunks are easier to swallow and remember. That makes intuitive sense. You're giving the system less opportunity to filter things out before the end.
Exactly. But what's fascinating here is what happened when they changed the type of data they fed it. They tested BERT on a math-specific dataset called FineMath and compared it to a general web text dataset called FineWeb. On the FineMath dataset, the memory recovery accuracy nearly doubled across the board.
Doubled. Just from switching from reading internet articles to reading math equations. Why is the AI's memory suddenly so much sharper when it's looking at numbers and symbols instead of a blog post?
It comes back to that concept of entropy we talked about earlier, or the inherent chaos in the data. Human language on the open web is wildly diverse, unstructured, and full of slang, idioms, and unpredictable tangents. It is high entropy data.
Right. Very messy.
Exactly.
Yeah.
Mathematics, on the other hand, is highly structured, rule-bound, and far less diverse in its vocabulary. Because it operates within strict logical constraints, it is low-entropy data.
Ah, I see where this is going.
Yeah, it takes significantly less computational effort for the model to perfectly compress and invert a rigid math equation than it does to map out a chaotic, winding paragraph of human text.
Okay, so we've established a pretty clear, if somewhat grim, reality about the standard models we all use. They have terrible memory. Scaling them up to massive sizes doesn't fix it. And unless we are only uploading pure low-entropy math, the AI is losing the vast majority of our document.
That's the state of things, yes.
But we also know that autoencoders can form perfect memories. So how do we actually bridge this gap? How do we build a useful AI that can predict natural language answers to our questions, but also remember everything we feed it with the efficiency of an autoencoder?
So this is where the IBM researchers proposed a brilliant hybrid solution. They designed a parallelizable encoder-decoder memory architecture. And the true beauty of this proposed system lies in its computational efficiency.
Efficiency is key when you're talking about models this big.
Oh, absolutely.
Yeah.
To appreciate it, we really have to look at how current models handle text. Right now, when you feed a full document into a standard transformer model, the computational complexity scales quadratically, what computer scientists denote as big O of n squared.
Okay, let's break that O of n squared notation down. That means if the length of the document goes up, the computing power required doesn't just increase at the same rate, it skyrockets.
It shoots up.
If I double the length of the document I give the AI, the amount of math the computer has to do quadruples.
Exactly. And if you make the document 10 times longer, it takes 100 times more compute. That quadratic scaling is exactly why massive context windows take so long to process and require unbelievably large amounts of server cache. It just becomes unsustainable.
But this new proposed architecture changes that.
It changes the game completely. Instead of forcing the model to process the full massive context all at once, the system chunks the text into smaller segments. It then uses an autoencoder to compress those segments into highly dense memory embeddings. By doing this, the researchers drop the computational complexity down to O of n to the 4/3.
Wait, let me actually do the math on that to make it tangible. So if O of n squared means a document that is 10 times longer requires 100 times more computing power, then n to the 4/3 means that same 10 times longer document only takes about 21 times more compute.
Right.
That is a massive, massive savings in processing power, which translates to what exactly for the end user?
For you and me, it translates to a significantly lower time to first token, meaning the AI starts answering your prompt much faster.
Oh, nice.
Yeah, and it also vastly reduces the memory cache sizes required on the server side, which lowers the cost and energy consumption. It makes the entire system exponentially more efficient.
But there is a catch here, right? If you just take a perfect memory autoencoder and wire it directly into a next token predicting causal decoder, they don't magically cooperate. I assume the model just gets confused.
Oh, they fight each other. If you just slap them together, the causal decoder gets lazy. It is already so good at guessing the next word based on its massive training that it just relies on its own internal language skills and completely ignores the rich, dense memory embeddings you're trying to hand it from the autoencoder.
It just defaults to what it knows.
Exactly. So to solve this friction, the researchers utilized a training breakthrough called curriculum learning.
Here's where it gets really interesting.
It is an incredibly elegant training pipeline. First, they take the high-fidelity autoencoder and they freeze it. They lock its parameters so it only does one thing: create perfect memory embeddings.
Okay, step one, freeze the autoencoder.
Then, they take the causal decoder and they essentially blindfold it. They force the decoder to practice a very specific exercise called a blank copy task.
A blank copy task.
Yeah. They feed the decoders the dense memory embeddings, but they completely mask out the original text tokens. Okay. The decoder has to learn to predict the text using only the compressed memory embeddings without leaning on its usual language guessing tricks.
I love this approach. It's like teaching a master chef who has gotten a bit too reliant on their favorite shortcuts. First, you take away their ability to just throw familiar things in a pan. You blindfold them, put 50 different jars of exotic spices in front of them, and force them to identify every single ingredient perfectly by smell alone.
That's a great way to look at it.
That's the blank copy task. You don't let them even attempt to invent a new recipe, which is the next token prediction, until they have proven they have a flawless working knowledge of the raw materials sitting right in front of them.
The analogy holds up perfectly. You are forcing the model to master the extraction of information from the memory embedding first. Once the decoder masters that blank copy task, then you lift the blindfold.
And let it cook.
Exactly. You introduce the combined objective function. Now, the model is allowed to use those rich memory embeddings while also doing its standard next token causal prediction.
And does this hybrid approach actually work? Like, does the AI remember the text while still acting like the conversational, helpful assistant we're used to?
The data proves it works beautifully. The combined objective function successfully trains the AI to copy perfectly and predict causally. It drastically improves the model's performance on information retention benchmarks, and it does so without ruining its general language understanding abilities. It fundamentally rewires how the model utilizes its memory.
This all sounds amazing in a research lab setting, surrounded by GPUs and data scientists. But for the person listening right now who is just trying to get their work done, how does this rewiring of AI memory actually change the tools they use every single day?
If we connect this to the bigger picture, the most immediate and profound impact is going to be on retrieval-augmented generation. commonly known as RAG.
RAG, right. That's the technology running under the hood of almost every chat with your PDF tool or the enterprise internal search engines that companies use to parse their own archives.
Yes, it's the backbone of modern AI search. Current RAG systems work by taking your query, say, what was our Q3 revenue in the European market, and attempting to match it against target documents using embeddings.
Okay.
But if this paper just proved that standard embeddings inherently contain only a tiny fraction of the original input information, it explains exactly why retrieval tools are so frustrating to use right now. It is the mathematical reason why they constantly miss specific, arbitrary facts buried deep in long documents.
Because the system is essentially trying to search through a massive library where 95% of the ink has faded off the pages?
Exactly. The standard embeddings are inherently lossy. They've thrown away the granular details during the compression process. Until these retrieval models learn to retain arbitrary information exactly like autoencoders do, they will always hit a frustrating performance ceiling. No amount of tweaking the search algorithm or adjusting the prompt will fix the fact that the underlying data representation is fundamentally incomplete.
So, what does this all mean? It means the comforting assumption we started this deep dive with, that the AI reads your uploaded document and keeps a flawless photographic memory of it, is completely false today.
Sadly, yes.
Right now, it's basically just skimming your document, getting the general gist of the topic, and tossing the fine print in the trash to save its own brain power. But this IBM paper isn't just pointing out a flaw, it is the actual blueprint for giving AI a true photographic memory.
That's the real takeaway here.
By using curriculum training and combining the perfect recall of autoencoders with the predictive power of decoders, we can finally build tools that don't just skim, but actually retain every single word we feed them.
And importantly, do it with incredible computational efficiency. It is a massive paradigm shift in how we structure the foundational models of the future.
We started by talking about that trust we place in the machine when we upload a PDF. Right now, that trust is misplaced. The digital filing cabinet is actually full of holes. But this research points to a very near future where that assumption finally becomes reality.
It's coming faster than we think.
Which leaves us with something genuinely fascinating to think about as we wrap up. If we succeed in making these new combined objective memory models the absolute industry standard, if we reach a point where every AI you interact with has absolutely flawless, lossless recall of every single word, document, conversation, and context you have ever fed into it over years of use, how might that change the boundary between an AI that is simply processing our data and an AI that truly knows our most nuanced, complex lives? It's a completely different kind of intelligence. Thank you for taking this deep dive with us.